let's go back to this problem and repeat it again using a t-test. Okay. So now, what would be the difference here using a t-test? Let me see. Let me get a fresh piece of paper and put this over here and see if I can. Yep. Okay, this time I'm going to say that the standard deviation for our sample is 7.1 instead of our population, right? So when I take a sample, right, I expect that sample, the mean of that sample is going to approximate the mean of what? The population. When I take a sample and I analyze that sample, I expect the standard deviation of that sample to approximate the standard deviation of the population. Bigger the sample size is, the more confidence I have in the mean and the more confidence I have in the standard deviation. We mentioned that sometimes you take a big enough sample that the t-score and z-score get pretty close and stuff like that. And we threw around a couple of numbers and stuff like that. I think one of the numbers we threw around, sample size is bigger than 30. We might just, at least in our preliminary analysis, we might use the z-score, the z-table anyway. I'm going to make this sample size instead of 29, I'm going to make it 25 to remove any doubt. With a sample size of 25 and not knowing the population standard deviation, should I use the z-score or the t-score? Okay, so now let's take a look at our 5 things we want to do. First thing I want to do is state the null and the alternative hypothesis. Okay, so I'm going to write those in here, H0 and H0. Okay, what's H0? What do we expect the mean to be equal to? 5. What's H0? Not equal to 5. Right, it's either greater than 5 or not equal to 5. What's our sample size? How much? 25. I'm going to change one more thing here, please. Oops, I'll turn that off. I'm going to make the standard deviation 4.1 instead of 7.1. Our standard deviation for our sample was 4.1. Okay, what's our standard error? Going to be equal to 4.1, right? That substitute for our sigma, we don't know what sigma is, over the square root of 25 is equal to 4.1 over 5. What's that? 0.82. Okay, that's our standard error. Okay, so now let's figure out how different. What was our x bar? Is equal to 6.7 pounds. Right? Let's figure out how many standard deviations apart that these two values are. Okay, so x bar minus mu over the standard error. That's equal to 6.7 minus 5 over 0.82 equals what? Equals to 1.7 over 0.82. What I got there? Is it 2.07? Ooh. Now, if I was using the z-score, I'd be feeling pretty good now, right? Because what is that? Since it's bigger than 1.96, what does that tell you if I was using the z-score? That the probability of my getting this extreme of value is less than 2.5% on either side. And I know that I got a p-value, a probability of being wrong, that's less than my alpha. Just as I was saying, let's go through our steps. What did I do? I just took off and didn't do anything, right? What's our significance level? What's our level of acceptable error? Alpha. What is it? Alpha is 0.05. Right? Okay, I should have done that, right? Draw a sample size n. We did that. Normal distribution. Use the t-distribution when you have to estimate sigma. But that's what we're going to do. Determine the p-value. Now we're going to determine the p-value. If it had been a z-score, we're home free already. Now let's take a look at the t-table. Okay, and I'll see if I can't open that on here. I don't know why I can't. 2.064. Okay. Wow. Okay. 2.064. In other words, the level at which we would have to, the number of standard deviations away from the mean we would have to be in the region of the distribution. Remember, every time, whenever we're using the t-table, we have the normal distribution has, or z distribution, has a certain shape, right? That shape gives us our 1.96 above and below the mean for our 95% confidence interval and for our alpha of 0.05. Any of the t-distributions, all the t-distributions, all have their own shape based on the degrees of freedom. If it were 5 degrees of freedom, right? In other words, a sample size of 6, it might be much wider, something like that. Be much broader. So in order to get to that 5%, we have to be further out. We have to have a z-score that's further out. Anybody think of a good name for what this z-score, good name for that z-score? That's the z-score for this sample size that we have to be bigger than to be outside of that 2.5% on the bottom and 2.5% on the top. That's an important z-score. That's a critical z-score, right? That's our critical value. We know if we exceed that t-score, right, that we have 5%, less than 5% chance of exceeding that t-score, or being smaller than that t-score on the other side, on the negative side, if the population mean, the mean of these two groups is really both 5. Right? We have, so have we exceeded that z-score? Right? So do we know what our p-value is? What's our p-value? We don't really know it. If we had when we did the z-table, we could look it up. But now that we're using the t-table, we don't have a table for every value. All we have is the critical value. So I can't say, like before, I could say that the p-value was 0.18, like probability of getting that extreme of value being outside of that, having a mean outside of those values, right, was 18%. Here I can't say that, but what I can say is that it's either equal to, less than, or greater than 5%. In this case, is it less than my p-score, my p-value, probability of getting that extreme of value if I don't reject the null hypothesis? Is that p-value less than, equal to, or greater than 0.05? It's less than. Our p-value, our probability of being wrong, is less than 0.05 because we've exceeded the critical value. Right? Yes. Okay. So I was hoping I'd get you confused somewhere. I was disappointed I hadn't done it earlier, but go ahead.
Right. So I was thinking that in this case, we would not be able to reject the null hypothesis because 2.07 is bigger.
Remember, bigger means 2.07 is is the number standard deviations difference between our sample mean and the population we're comparing it to. Right? So that means I'm further out on my distribution, which means that it's less likely I would get that result if the mean were really 5. Right? So less likely is good because that allows us to reject our null hypothesis. So we want our t-score to be bigger than our critical value for t. Right. Remember that 2.064 represents a probability of being wrong when you say the two means are different of exactly 5%. If you're further apart, you have less chance of being wrong if you reject the null hypothesis and say that the two distributions are different.
I don't even know how to express that.
Okay, let me put it another way. Let me get another piece of paper here. No, this is worth doing because if you understand this, remember we're strictly doing single sample tests here, right? When we do, I'll talk about excuse me, single sample tests, and for the most part, right now we're concentrating on a two-sided, not single-sided. So we're automatically yeah. Hang on a second. Hang on. Wait. Let me do this. Here's our normal distribution, right? Now this is a mean of 5, right? And I said our whatever our standard error is. Say what did I say? A standard error is equal to 0.82, 0.82, something like that. Well, if we knew sigma, right, we would say that that my probability of getting a mean, if I were drawing it, if this population really had a mean of 5, if that was truly true, null hypothesis is true, if that were true, the chances of my getting a mean for a sample of size 25, the probability of getting a mean that's bigger than 5 plus 1.96 times my standard error, 0.82, the probability of getting a mean bigger than that, in other words, basically bigger than around 7 or something like that, probability of getting a mean bigger than that is only 2.5% or less, right? Okay, so now if I knew this, if sigma was if I really knew sigma, and that's how I got my standard error. If I took a sample of size 25 and I got this result that was bigger than this value, so say 7.1, I'm so far away from 5 that the chances of my getting that higher value from this population, had that really been had this distribution really represented the population, probability of getting that value would be less than 2.5%, right? And I again, because I didn't make the assumption higher or lower before I took my sample, I could have also gotten an extremely low value. I would say whatever that was, if that were 1%, then I would take 1% on this side too, and say, oh, it could have been lower too, and just add them together.
I get that 2.07 is bigger
Okay.
than 1.96.
So now what I just did now was instead of using the Z table, I used the T table. Okay. So now what did the T table tell me? For a sample of 24 degrees of freedom, sample size of 25, instead of looking like that, it was wider. So in order for me to get a value that's outside of this boundary, so this is 2.5%, and this is 2.5%. Well, my Z-score, right, or T-score in this case, my T-score, my minus T-score, right, would have had to have been 2.06, right, instead of 1.96. Now, what was the actual T-score that I calculated for this? It was 2.07. So where's 2. It's out here. So it's less than 5% chance of me getting that extreme a value if this population was really true. If this population mean was really true. Just like it was less than 5% chance of getting that sample from our previous one where we knew this population standard deviation. The main effect of using the T instead of the Z is it made us have to be more rigorous. In other words, it made us have to have a bigger difference from the mean in order to have that level of assurance that we have less than 5% chance of being wrong. Remember, I could get any one of these values from this population. I could take a sample of size 25, and I could get a mean of not just 7, I could get a mean of 8, right? How likely is that? Very unlikely, right? Way less than 5%, but probably way less than 1%, right?
Right.
It's very unlikely that would occur. See, with that, it's more obvious. This is close.
I get all of that too.
Yeah.
I guess then the part where I'm confused then is how that relates to the p-value.
Oh, the p-value is the probability of getting that value or higher.
Okay.
And that value or yeah, that value different or higher, or on the other side, that value or lower. So the p-value would be, let's say, see now, let's say 2.07 is what I got. I know that's far enough out that it's less than 2.5% on this side. But what is the actual percentage? What's the probability I'd get a value as high as 2.07? Well, I know it's going to be less than 2.5, right? That area is going to be less than 2.5, but not much because there wasn't much of a change. So I'm guessing it's around 2.4, right? So our p-value would be this area that's represented by the t-score of 2.07 doubled, right? Because you're doing it on this side also, right? So that would be probably a p-value of 0.048, 0.048, let's say, right? Now, that p-value is less than alpha, right? That p-value is less than alpha. So that means there's enough difference that you could say that's less than my level of error I'm willing to accept. So I'm going to reject my null hypothesis and say these two groups are different, that it wasn't really from this population. It was from some other population, just happened to grab the tail.
So if we use the t-score, we have to guess the p-value.
Well, you don't know it. All you know if you use the t-score is that your p-value is less than 0.05 if your z-score exceeds that. Now, next week, when we do this again, we're going to use SPSS again, right? Because SPSS, remember I mentioned to you about SPSS? SPSS doesn't believe in the z-table ever, right? SPSS always calculates a t-score, right? SPSS will say to us, well, remember, one of the reasons we're doing this is because what we really need to figure out the percentages for the t-scores, right? We need a t-table that looks just like the z-table. We need a table like that for every sample size. 2, 3, 4, n equals 27, n equals 35, n equals 107. We need a book of t-tables, right? We don't have that available. We only have a one-sheet table that tells us what the t-score has to be so that we know whether or not we've exceeded that 5%. If we measure the z-score, we know what the p-value is exactly. If we use the t-score, all we know is we either exceeded the p-score or the p-value is less than 0.05 or greater than 0.05. Or for that matter, remember there's a few columns there. Your p-score could be less than 0.01 or greater than 0.01 and so on and so forth, right? Because those are what those scores represent. But SPSS is not going to do that. SPSS is going to actually give you a p-value. So for instance here, it will tell you the t-score is 2.07 and the p-value, two-sided p-value, is 0.048, right? It'll actually give you a value for that. In fact, maybe I even have let's do one. Let me get this out of the way. Let's actually do one. Boy, this is taking longer than it always takes. This in next week, this in next week's session are going to be, I think, a little bit challenging but it's going to be really rewarding because this is really getting really nitty gritty here. This is stuff you're really going to be able to use. In other words, if you do a study, this is what you'll be actually doing. Next week, it's going to get more complicated. One of the reasons it's going to get more complicated is let's say that instead of doing this kind of bogus, I'm going to compare a value to a population, right? And instead of doing that kind of bogus thing, I'm going to do something that's more likely to happen where you don't know what the population mean is for either group. In other words, you take a placebo group for a drug, and you take for a blood pressure drug, and you take a drug group, and you see how much the blood pressure changed or something like that. Well, now you got two groups. Now you got one set of numbers for this group, one set of numbers for this group, and you want to compare the two of them. Well, remember we talked about the idea of you could calculate confidence and you could calculate confidence intervals through them, and you could see if they overlap. But there's a problem with that, and that is your null hypothesis is what? That they're not different, right? That they're really from the same population. Well, doesn't that mean that you should also probably say, well, that if they're from the same population, they should have the same standard deviation, right? Sigma. for the two populations. Well, I don't know the population standard deviation. I only know standard deviation for this sample and for this sample. And if I calculate a confidence interval, I'm assuming with this sample that that population has one standard deviation, this one has another. So I'm not really comparing apples and apples anymore, right? So now I got to think of some better way to do this. And you say to yourself, well, gee, which standard deviation should I use? The one from population A or population B? From placebo or from drug group? Well, you say to yourself, well, gee, since I'm assuming that they're from the same population to start, maybe I should combine the two of them, right? Things are going to start to get a little complicated now. Should I assume that when I look at these two standard deviations from the two populations and they look pretty close, then it's easy to say, yeah, I'm going to combine the two of them, two groups, and use a single standard deviation for the two of them. That's, but what if one of them standard deviation comes out to be 3 and the other one comes out to be 11? And you say to yourself, boy, it seems like standard deviation from these two groups, whatever populations they came from, maybe they're the same, maybe they're not. But I sure looks like I got different standard deviations from these two groups, right? So now you got to decide, how am I going to handle it if I think they're the same and I think they're different? This is where you're going to fall in love with SPSS. Because trust me, if you had to do this yourself, you'd want to shoot yourself in the head, right? This SPSS is going to be a godsend to you now for some of these, for a lot of these calculations, right? What's that? Yeah, trust me, the first couple of semesters I did this, I wanted to, but that's a whole other thing. But at any rate, I've been doing this a long time now. I've gotten over that. I've gotten past that. So at any rate, so those kind of calculations, and we really should work through how to do those calculations at some stage. Maybe we'll have an online session where we just actually do those calculations for small groups by hand so you can see what's happening. But in real life, you're going to use software to do this most of the time. So next week when we pick this up, we're going to be looking at a lot of other possibilities here. Two groups, two means, two standard deviations, similar standard deviations, different standard deviations, so on and so forth. So we're going to be looking at a lot more stuff here. I'm going to post some examples that you might want to try before next week, so we get at least this single sample stuff done. But let's take a look at SPSS. I'm going to open up SPSS. Let me find. Actually, I got some. I think I have. I forget what this particular why I put this one on Blackboard, but here's one sample. Okay, should start up. Come on, today, please. Yep, it's bouncing. That's a good sign. Okay, it opened several times, of course. Okay, so here is a database representing 16 samples of sandwiches. This is the number of slices that came out of Ben's Delicatessen of corned beef. Sometimes, sometimes they put a lot of slices, sometimes they don't put many slices, right? So I'm going to just do some basic descriptive statistics as we did before. Analyze, descriptive statistics. I'm going to go to Explore. It'll give me more information. I'm going to move slices, numerical variable, into my dependence list. I'm going to tell it I wanted to do basic descriptive statistics, and I'm going to say OK. Okay, let's see what I get. I get a delay. I don't know what it could be doing all this time at 8 bazillion operations per second. You would think it would come out. Oh, maybe it didn't. It's behind here. There it is. Okay. So what's the mean number of slices that you get from Ben's Delicatessen? Okay, given a sample size of 16, oh, it's 10, right? Now, I happen to know that across the entire city, you get, let me just take a quick look at this for a second. I happen to know across the entire city that delicatessens give an average of 8 slices, the entire city. I want to test whether or not Ben's gives a different number of slices than all the rest of the delicatessens in the city. So, what is my median? What am I comparing Ben's to? I'm comparing Ben's to 8. So my null hypothesis is mu is equal to 8, right? So now I analyze this. Now, I don't know the standard deviation for the entire population of delis in New York City. So I have to calculate this from our from our sample. So if I look at this more closely, I see that the mean number of slices that I got on my sample of 16 random occasions from Ben's was 10 slices per sandwich. Sometimes I got more, sometimes I got less, right? And what was it? Sometimes I got 7. One time I really got chipped. I only got 4, right? So there's some amount of variability here, and that variability is represented by the standard deviation, which is 3 slices, right? Okay, so now I'm going to say to myself, okay, it looks to me like you get more corned beef at Ben's on the average than you do from all the other delis in New York City. The average for all the other delis in New York City. That's the way it looks. But it could be that my sample of 16 is not a very big sample. My sample is 16. I just happen to be lucky and get more than usual at Ben's. So I need to know whether that 10 is different enough than the average for the rest of the city of 8 to be able to say with 95% certainty, or what alpha is equal to 0.05, less than 5% chance of being wrong, that there's a difference between what you get from Ben's and everywhere else. Notice I kept it two-sided. I didn't say you get more from Ben's. I didn't say you get less from Ben's. In fact, I would have made what should I have done first? Shown you this data or give you my hypothesis? Should have shown you my hypothesis, so you didn't know whether you got more or fewer slices. That's really why we do it two-sided, because it just occurred to me now. I have been showing you the data before we made up our hypothesis, right? In other words, going into this study, we might not have known. We just might have said we're going to sample Ben 16 different days and see what we got and compare it to the rest of all the other delis, right? So that's the point of being two-sided, right? So now I come up with 10. Now my problem is 10 different enough from 8 in a sample size of 16 given a standard deviation of 3 slices? Is that different enough for me to say that that difference is not due to chance and that Ben's gives you the same amount as everybody else? Or can I say with 95% certainty, 5% chance of being wrong, that it's really a different enough number? If I knew the true standard deviation, right? If this standard deviation was the true population standard deviation for the whole city, 3, if I would have needed how many slices would I have needed difference from 8 in order to reject the null hypothesis? I would have needed 2 times that standard. I'm sorry, it was a sample size of 16. 3 divided by the square root of 16 divided by 4, approximately 1. I would have needed, let's see, if we knew the standard deviation, I would have needed 1.96 times 1, or 1.96, added to 8 and taken away from 8, right? Actually, added to 8 and taken away from 8 in order for me to say that Ben's is different than 8, right? So now I'm going to actually, since that's the way I would have done it before, we would have calculated, X bar, which was 10.06 minus 8 over the standard error that I calculated because I knew that 3.1 was sigma, and so on and so forth. And then I go to my z-table. But now we're going to use SPSS to do it using the t-score, right? So not assuming that. In other words, SPSS not going to use the z-table, going to use the t-score, and it's going to do it whether the sample size is 16 or the sample size is 2,000. So now I'm going to go up here, and I'm going to say to myself, well, now I want to do a test. I want to compare whether or not I am enough standard deviations apart to reject the null hypothesis, have a probability of getting this extreme value that's less than 5% of the time. Okay, so I'm going to go up here to analyze, and I'm going to go up here compare means. Isn't that what I'm doing with comparing the means? And I'm going to go to one sample t-test because I'm comparing one sample to the entire population. Okay, so I'm going to move my slices in here. That's my test variable, and I'm going to compare it to what I believe the population mean to be, which is 8. I'm comparing my mean of 10.06 to my population mean of 8, and I'm going to click OK, and SPSS is going to go ahead and do that t-test for me. Let's see what I get. I'm going to do this and move this up. My t-score is 2.636. I'm feeling pretty good, right? However, it's a relatively small sample size, right? If I looked up how many degrees of freedom is 16, sample size 16, 15. Okay, if I look up what's the critical t value for 15 degrees of freedom, and what's that? 2.13. So it looks like my two values are far enough apart that I can say that I've exceeded the critical value and there's less than 5% chance of getting this result if in fact Ben wasn't any different than the rest of the city. Yes. Yeah, it is. It's 2.6. No, it's 2.63. 2.63. You can't see that well, right? Is that it? Yeah, I can't. Yeah, there's a way for me to zoom this out, but I have to change the accessibility settings. So that's 2.63. So this is bigger than that. Okay, in fact, not only is it bigger than that, but it's actually going to calculate the actual probability of getting that result, that extreme result, a result that's 2.6 standard deviations apart, t-scores apart. Okay, degrees of freedom is 15. Significance, instead of calling it the p-value, SPSS calls it the significance or statistical significance. And what does it say the two-sided significance is? It's 0.019. Notice it said that's the two-sided. That means it's already taken that area on one side and doubled it, so you don't have to do that again. That's the actual p-value. You don't have to multiply it by anything. If you use the z-table, you do, because it only gives you one side of it if you're doing a two-sided test. Okay, the mean difference was 2.03 and the 95% confidence interval for the difference between the two. Now here's where you can kind of apply the confidence interval. What they've done here is they've analyzed the 95% confidence interval for the difference between Ben's and the other delis, right? And the difference should be, if there's no difference, the difference should be 0, right? And in fact, we're 95% sure that the real difference in the number of slices is between 0.39 and 3.73 slices, right? The middle of that was 2 slices, the difference that we calculated, right? So what number is not included in the range 3.39 to 2.0? So since 0 is excluded from that confidence interval, we can say that the difference is different than 0. So that's a way you can still use a confidence interval to kind of change that. And in fact, we're going to look next week at what are called paired samples, where we do exactly that. For instance, if I were to take you and have you take, let's see, take a drug, for instance, and eat 10 grams of candy, take a drug, eat a diabetes drug and eat 10 grams of candy or something like that, and measure your blood sugar and so on and so forth. I might measure you without the drug, how much your blood sugar goes up with 10 grams of candy. And I might tell you, come back and I'm going to measure the same person with the drug and then eat 10 grams of candy. So now I see how much it went up in one case, how much it went up in another case. So instead of looking at that as two separate numbers, for each person, I'm going to look just at the difference, right? And let's say that for you, when you took the drug, your blood sugar went up 10 less, minus 10. For somebody else went up plus 4. Somebody else went, right, so on and so forth, right? And then I'm only going to look at the differences, right? And I'm going to compare that to my null hypothesis that the drug didn't make any difference, that the difference is equal to 0. And so that's really almost like the confidence interval, right? But we're going to look at that also. So this is the way. So my t-value is 2.636. We could actually calculate that, right? We would actually, we'd say, okay, 8 minus 10 point whatever it was, 10.1 divided by the standard error, which we would calculate as, I forget what it was. Calculate as 3.1 over the square root of 16, which is 4, right? And then take the difference between 8 and 10.1 and divide it by the standard error, which whatever that was, I guess about 2 or something like that, and get our t-score. And if we did that, then all we'd be able to say is that t-score is bigger than what we need to reject the null hypothesis, that there's 5% chance or less than 5% chance of getting that extreme result if they're from the same population, if the mean is really 8 slices. Right? But with SPSS, we're able to do a little bit more detailed analysis and actually calculate the p-value, which is nice because now we know not just that we are less than 0.05, but there's less than a 2% chance that we are wrong, if we reject the null hypothesis. Okay?